Hello everyone, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss another very important topic from the 2D NMR spectroscopy, and the name of the topic is the interpretation of Noesy spectra, Noesy, Noesy spectra, and where Noesy stands for the nuclear Overhauser Effect Spectroscopy. If you see here, Noesy, which means nuclear Overhauser Effect Spectroscopy, where Overhauser is the name of the scientist Albert Overhauser, because he actually Overhauser used the particular concept in this particular spectroscopy. That's why to honor him, actually this is known as the known after his name, right? So little later I'll discuss what is the concept actually used by the Overhauser here. But before going into the details of your Noesy spectroscopy, first of all I am going to tell you from the last 2-3 lectures I am discussing your homonuclear 2-dimensional NMR spectroscopy, and so far I have covered two very important interpretation, right? First, interpretation of COSY spectra. Again, this COSY spectra gives the correlation between your hydrogen and hydrogen, proton-proton correlation is there. And second, then in the last lecture I have discussed the interpretation of COSY spectra, and that COSY spectra again actually discuss the correlation between the proton and the proton. Okay, so if you are watching this video for the first time and you are new here and you want to learn the interpretation of the COSY and the COSY spectrum, so you can check in the description box where I have given you the links of the above two lectures. Watch those lectures and understand how we can differentiate between COSY and the COSY. Okay, so now my today's topic is the interpretation of Noesy spectra, nuclear Overhauser effect spectroscopy, right? And so first of all, what is the use of the Noesy? Again, it is you see this Noesy is also your homonuclear correlation. That means again we are discussing the correlation between the hydrogens. Of course, this hydrogen correlation, this hydrogen correlation would be different what we have learned in the COSY as well as in the COSY. Okay, so first very important point which you must remember, Noesy spectra can be used to determine the stereochemistry of the compounds. For example, if you have say relative, if you want to know the relative configuration of your doubly bonded compounds, like compound just if whether you want to know, if you want to know whether your compound is your cis or the trans, then this Noesy spectra very beautifully explain this, right? So example, relative stereochemistry around the double bonds, right, cis trans system. And if you want to know the relative stereochemistry of certain groups at the junction of the ring, then again this stereochemistry, this spectroscopy is very, very important. And if you have the cyclic compounds and you want to know the proximity of the substituents in the cyclic compounds, right, then again this Noesy spectroscopy is very, very important. But most particularly, as you have seen here, this Noesy spectra are of particularly useful when you actually want to know the 3D folding of the biomolecules, especially for the proteins. So the persons who are working in the field of the proteins, they know the importance of the Noesy, right? So I will also explain you how this Noesy is useful in case of your biomolecules, right? So but first point you should remember, right, relative stereochemistry you want to know.
और कोई साथ में नहीं होता है, नहीं यार वो
अब यहाँ से देखिए ये मंदिर हमें साफ दिख रहा है। तो ये देखिए साथियों, ये जो है इसका मुख्य मंदिर और पुराना मंदिर है। ठीक है, पानी के नीचे भी जाके ये वीडियो। हेलो दोस्तों, देवलोक में आपका स्वागत है। तो आज के व्लॉग में हम बनाने जा रहे हैं and the second this is known as the nuclear Overhauser effect spectroscopy, and as I already told you, this Overhauser is the name of the expert. Actually this the theory of dynamic nuclear polarization. Let's see, there is a concept of the dynamic nuclear polarization, right? And that theory of dynamic nuclear polarization was used by the Albert Overhauser. So basically, initially what happens, basically in the metals actually, right? See, when you have the metals, what can do, if you have an NMR active metal, it can transfer its polarization to another another metal, which is that metal is also NMR active, right? So both nuclei must be active, and you can transfer the polarization from the one nuclei to the other, but the condition is that this magnetization transfer actually, right, will occur between the nuclei only when they are in very close proximity. They must be very close to each other, right? So I am not going into the detail of this. If you want to know, then you can learn any your physical spectroscopy, physical NMR spectroscopy, or what you can do, you can also follow the NMR spectroscopy lecture by Hanudatta Attatray, Professor Hanudatta Attatray from ISC Bangalore. Actually, he explained all these things in detail in your lecture. But my cup of tea is the interpretation of the Noesy spectrum. So I am not going into the detail of the dipolar interaction actually, right? So dipolar interaction, I already told you, the transfer of the magnetization from one active nuclei to the other active nuclei. This is something very important, right, which you should know. And the important thing is that the interacting nuclei should have a very close proximity of 5 to 6 angstrom, right? See, only if you have the two interacting nuclei like two hydrogens, so in that case these two hydrogen must be in this range, their distance actually must be in this range, proximity should be in this range. And the very important thing is that, see, in the COSY you have seen that only those nuclei will couple or will give the cross peaks actually in COSY, which actually are J coupled. That means 1 bond coupling, 2 bond coupling, 3 bond coupling. Only those kind of the nuclei will give the cross peaks in the COSY. And if you have if you know the TOXY, then in the TOXY there is no such condition like 1 bond or 2 bond coupling. Long range coupling can also be observed in the TOXY, that is total correlation. But in the Noesy spectroscopy, the nuclei may not be it is not necessary that the nuclei are connected with certain bond. So basically this nuclear Overhauser effect spectroscopy, the transfer of magnetization actually occurs through the space actually. That means two hydrogens, when they are not actually connected with the bond, then they show the cross peaks. Okay, remember this point. I am going to explain this with the help of the example very soon. And then you see, based on the proximity, the intensity of the cross peak would be there. See, in the 2D NMR spectroscopy, especially in the Noesy, it is sometimes like that. One peak is very sharp and other peaks very not that sharp. Why this happens actually? So you see here, if you want to know the proton proximity in angstrom, so if this is 3.5 angstrom, that means two protons, their proximity in the space is of the order of 3.5 angstrom, then you will get the very strong cross peak, very sharp, very strong cross peak. But if this distance increases and goes up to 3.5 to 4.5, then you will have the medium intensity cross peak, right? The intensity is not that good in that case. But when this proximity between the two hydrogens increases from 4.5 to 5.5, then you see the very weak peak would be there, and it is sometimes difficult to assign those peaks, right? So it is quite clear now that if you are getting the very strong cross peak, it simply indicates that the interacting nuclei are in this particular range, right? This is something very important which you should know, very important. Okay, so
आज जैसा और कोई साथ में नहीं होता है, अरे नहीं यार वो
अब यहाँ से देखिए ये मंदिर हमें साफ दिख रहा है। तो ये देखिए साथियों, ये जो है इसका मुख्य मंदिर और पुराना मंदिर है। ठीक है, पानी के नीचे भी जाके ये वीडियो। हेलो दोस्तों, देवलोक में आपका स्वागत है। तो आज के व्लॉग में हम बनाने जा रहे हैं सी व्हाटएवर आई हैव एक्सप्लेन्ड सो फार, Now we'll apply this knowledge on the spectrum. So okay guys, this is the Noesy spectrum, and say this is your F1 dimension and this is your F2 dimension. In F1 dimension you are having the chemical shift of the protons, and F2 dimension you are also having the chemical shift of the protons, right? And then you are having the diagonal. This is your diagonal. So diagonal is nothing. You can see here how many different kinds of the protons are there. This is methyl. I have given the number 1 to this methyl, 2 to this hydrogen, 3 to this hydrogen, and then 4, 5, 6, right? Because you see the plane of symmetry is there. That means 4 and 5, 4 and 5, this and this equivalent, this and this equivalent. So how many cross peaks? See how many peaks in the 1D NMR spectrum you will observe. You will see 1, 2, 3, 4, 5, 6. So 6 peak would be there. Now if you check here, this is your H1, this is your H2, this is your H3, this is your H4, this is your H5, this is H6. You know, if you come down here, you can see this is 7 ppm, beyond 7 to between 7 to 8 ppm. That means this area belongs to the aromatic protons, right? 4, 5 and 6. You see here 4, 5 and 6. So these are the aromatic protons which are concentrated here. And then you see H2 and H3, that means these trans protons, right? H2 and H3, they are trans to each other, okay? They are trans to each other, and these protons are here. You know, this alkene proton resonates between 4 to 6 ppm, or more precisely 5 to 6 ppm. So their chemical shift, you see, you can check here, it is somewhere around 6 point certain ppm, right? And then this is your simply aliphatic proton. So its chemical shift actually would be very low, somewhere around at 1 ppm, and you see here it is at 1 ppm. So for these protons, chemical shift are in this particular dimension, and for these protons, the same spectrum I have plotted here, right? And their chemical shift you can observe here. And this is the diagonal, okay? And in the diagonal you see the 6 peak, right? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Sorry, 1, 2, 3, 4, 5 and 6. This is nothing, right? You can see this is solvent actually. You see here residual solvent. This peak belongs to the solvent here. So ignore this particular one. Okay, you can ignore this one. So this is the diagonal. And see Noesy spectrum. Please remember, the spectrum is symmetrical with respect to the protons, right? Say here whatever the peak you will find here, the exactly same cross peaks would find in this lower terrain also. So it is up to you whether you interpret the upper part of this diagonal or the lower part of this diagonal. Both will give you the same kind of the information. Okay, now you can see here what is happening here. This hydrogen 1 and this H2, right? So this is 1 bond, this is 2 bond. Please remember, this is 1 bond, this is 2 bond, and this will interact actually. But this interaction, there is no need to count this bond because this interaction would occur through space. What is the meaning of that? The distance between these two should be very low. Okay, please remember, that means less than 5 angstrom. So these two would interact. That means you must find the cross peak which correlates the type 1 proton and type 2 proton. So let's check where they are actually. So you can see here this methyl, which I have numbered as one type of the proton, and this H2, there must be the correlation between the two, and we can approximate this thing, right? Because we know the one bond distance is basically 1.5. Okay, so if you count here, this is 1.5, this is 1.5, so total 3 angstrom is there. Okay, that means these two must be must be in the close proximity which is required by the Noesy spectroscopy. That means less than 5 angstrom. So there must be the correlation between the two. Okay, so I am this part and this lower trace of this Noesy spectrum, as I already told you, and this upper trace, both will give you the same information. It is up to you whether you interpret this part or that part. So I am going to interpret the above part of the diagonal. Okay, so I want to show or I want to see the cross peak which correlates these two, H1 and H2. So here you can see this is your H1 peak, okay, and that H1 peak is somewhere here. And if you go up, this is your H2. So H2, this cross peak, right, this one. So if you want, then I can mark this cross peak as 1. So this cross peak 1, this is only for the sake of the explanation, guys, please remember. So this H1 here is correlating with the H2. So this correlation is there. So what you can do, you can show this correlation, okay. So now what can happen, this H1 can also correlate to this one, because this is 1, this is 2, this is 3, this is 3 bond, and 3 bond, you know, 1.5 into 3, it is somewhere around 4.5, again it is less than 5 angstrom. So there must be the correlation between these two, okay. So 1 and 3, so there must be the cross peak which correlates 1 and 3. So here you can see this is the peak, right, this peak, right, this peak, this cross peak, where a small circle which I am calling as 2, okay. So this is actually, you see, H1 and it is correlating with the 3. This is proton 3, okay, and this is your proton 1. So here multiplicity is also given, but I am not going into the multiplicity detail. I am only explaining the correlation. If you want to know the multiplicity, then you can assign by your own, okay. So this peak is correlating H1 and H2, that means this correlation, and that peak number 2, it is correlating this H1 and H3, so this correlation is there. So what you can do, you can correlate these two also. Clear? Now it is quite clear. See, again you can approximate. If you want to know the correlation between these two, so this is 1, this is 2, this is 3, this is 4. So it is somewhere around 6 ppm, 1.5 into 4, that is somewhere around 6 ppm. So again it is in the range of this Noesy interaction, right, dipolar interaction. So there must be the correlation between these two. However, we can check the intensity also. Higher the intensity, that means the close the proximity. So there must be the correlation between H3 and H4. Okay, now you see this is your H3 proton at this lower peak, right, this lower peak. I am calling this peak as, say, 3, right, this peak 3, which is this one, that must correlate with the H4. So if you extend this line here, lower one, right, and go at the top, so it is correlating with the H4. So this correlation is there. So again, if this correlation is there, what you can do, you can correlate these two. On the same ground, what you can see here, this this H2 and this H4, again they are very close. In the picture itself, it is looking that they are very close to each other, right? When they are very close to each other, so there must be the cross peak which connects actually 2 and 4. So if you check here, this is where H2, the above peak. So I am calling this dot is the peak 4, and which is due to this cross peak which is correlating H2, right? And if you go up, right, here in the center, so it is correlating with the H4 again. So H2 is also correlating with the H4, okay. So because these two are same, right? So this peak actually is correlating these two. So 1, 2, 3, 4, total 4 cross peaks are there. That means 4 such interaction must be there in that case, right? So this interaction is here actually, right? So this is interaction number 1, this is interaction number 2, this is interaction number 3, and this is interaction number 4, and all 4 for all those 4 you are getting the cross peak. See how easy the Noesy spectrum is this, but the important thing is that you should know the intensity of the peak. It is very, very important. You should know the intensity, okay. Now if I write, say this is the different compound. See, basically if you come here, this is actually beta methyl styrene, basically trans beta methyl styrene. How beta methyl styrene? See, this is your alpha carbon, this is your beta carbon. Beta carbon is having methyl substitution, so you can write beta methyl styrene. Okay, styrene, you know, when you have this benzene ring, that is CH double bond CH2. This is styrene, and I have replaced this one H with the methyl, which you see here actually, right? And it is trans. It is trans. Okay. So when it is trans, so you can write here trans also. The moment you change the position of this hydrogen, so you can convert this into the cis beta methyl styrene.
आज जैसा और कोई साथ में नहीं होता तो अरे नहीं यार वो
अब यहाँ से देखिए ये मंदिर हमें साफ दिख रहा है। तो ये देखिए साथियों, ये जो है इसका मुख्य मंदिर और पुराना मंदिर है। देखिए पानी के नीचे भी जाके ये वीडियो। हेलो दोस्तों, देवलोक में आपका स्वागत है। तो आज के व्लॉग में हम बनाने जा रहे हैं। सो नेक्स्ट इज व्हाट यू सी हियर। अगेन दिस इज व्हाट सिस बीटा मिथाइल स्टाइरीन. So again you see the 1D NMR spectrum would look like same, but if you want to know the proximity of these hydrogens actually, right, then you must use this Noesy spectrum. So as I already told you, this 1 and 4, they are looking very close to each other, 1 and 4. So there must be a cross peak which correlates 1 and 4. So this is H1, okay. And this H1, if you go up, it is correlating with the H4. So this correlation is there, H1 and H4. So H1 and H4 correlation is there. Okay. Similarly, this H1 must correlate with this H2 also. Cross peaks must be there. Okay. They are again in the close proximity. So there should be a cross peak which correlates H1 and H2. So let's check. This is where H1. If you come here, and this is your H2, so this cross peak is giving you the correlation of this one. So this is H1 and H2. So we have done this, we have done this. Now you can see here, this since they are cis to each other, so they are again very close. But in the earlier case, if I go back, so since this is the trans isomer, so this actually H3 and H2, they are very far apart. However, their bonds are only 3, but you see they are very far apart, so they cannot interact. So we are not having the peak correlating H3 and H2. We are not having this correlating H3 and H2 anywhere. Okay. But in this picture you see H3 and H2, they are very close to, in the proximity. So there must be a cross peak which correlates H2 and H3. So we will check the H2. Where is H2? Say this is H2. If I come here, this is the cross peak, and if I go up, this is H3. So this is correlating this H2. Okay. So this I have again explained. Then there must be the cross peak which correlates H3 and H4. So again if you check your H3 which is this one, and if you go up, it is correlating with the H4. So you see how easy is this one. So this is how you can check. So this is just one example of your cis and the trans beta methyl styrene, how you can differentiate between these two isomers using this one. But again, if you have the cyclohexane type of compound, any cyclo compounds, and which is having the different kinds of the substitution, then again the Noesy spectrum or the Noesy spectra can be very beautifully used to explain the difference between the two, right? And as I already told you, this method is very particularly useful in the protein folding, right? Say for example, if you have say just like that, say this is say the protein chain, okay, and at the end you are having the methyl somewhere here and the methyl somewhere, and somehow it actually coils, and this CH3 and this CH3, they come closer to each other. So there must be the peak which correlate these two. So these things are utilized in the interpretation of your biomolecules, especially for the proton. So this is the idea about the Noesy spectrum. So guys, this is, you see, the students who actually were not aware about the interpretation of the 2D NMR spectrum, they generally think actually it is quite difficult, but believe me, this 2D NMR is not that difficult to interpret. Okay, as you have seen in case of the COSY and the TOXY, now in case of the Noesy. So that's it for today, guys. Okay, and again the same request I am making to you. See, if you are watching this video for the first time, please subscribe the Tetrahedral Chemistry classes and do share with your friends also. And moreover, I have also started a new channel which is known as that name of the channel is Devlog My Vlog. This is the daily vlogging, not exactly daily vlogging. I don't have that much of time to make a video or vlog daily, but because I have to give some time to the tetrahedron, see my main time to the tetrahedron chemistry classes, and then the spare time I do that vlogging apart from my academics and the teaching notes. So please subscribe that channel also and share with your friends also. I hope you enjoy the lecture. So we'll meet you in the next lecture with certain another important thing, right? Then that's it for today. Thank you very much.